Okay, this is going to be our last lesson for this little mini unit, and we're going to create functions this time from context. So we're going to be given a word problem, and then we're going to write the appropriate equation, whether it's linear, exponential, or quadratic. And then we can use our models, our equations, to make predictions, to answer questions. So let's just recall our three functions, and we will write our functions if linear in slope-intercept form, if quadratic in standard form, and if exponential, we're going to write it in our basic AB to the x. So in linear, remember our M is our constant rate of change, our B is our initial value when x is 0. In standard form for quadratic, A is our gravity factor, B is our velocity, and C is our initial height of the object. And then in exponential function, our A is our initial value when x is 0, and then B is either our growth or decay factor. So remember, we're just going to use the basic A, B to the x. Okay, I know that in lesson 8.1, we learned or recalled how to identify if a function table is linear, quadratic, or exponential. There is another method that tells us our function table is exponential. So let's just, and I'm going to have my calculator handy. And so let's find the first difference. So from 84 to 52, we are going down 32. And then from 52 to 36, we're going down 16. And then from 36 to 28, we're going down 8. And from 28 to 24, we're going down 4. Now you can see the pattern here. Okay, one, we know that it is not linear because it's not constant. And we can make sure it's not quadratic. Okay, or quadratic, that means we would have a constant second difference. So let's just, from negative 32 to negative 16, that's going to be negative 16. Then we're going down negative 8, and we're going down negative 4. And you can see that we have the same pattern. And you can see that it's going down by 1/2. It's being halved. So this tells me that this is exponential, and it gives me the B value of 1/2. Okay, now let's try a second one. So we're going from 592 down to 208. That is a change of negative 384. And then we're going from 208 down to 112. That's a change of negative 96. And then 112 minus 88, that's a change of negative 24. And then we're going down to 82, that's a change of 6. So minus 6. So we can prove that this is exponential by placing the difference over the previous difference. And if it's true all the way down, once we simplify, this is going to tell us that it is quadratic. And then that value that's constant, that constant ratio, that will be your B value. So 96 over 384 does give me 1/4, 1/4. The same for negative 24 for negative 96 is positive 1/4. And then of course, we get 1/4. So when you have a constant ratio, then we know that's going to be exponential, and that B value is 1/4. So I just wanted to share with you another way to identify exponential functions. Okay, here's our first example. Sophia dropped her iPhone from the rooftop of a building at 600 feet. The height of the phone after being dropped is given in the table below. What type of function would best describe the phone's height as a function of time? And then we're going to write a model to represent. So first, let's just find the first difference. Let's see what we get here. So this is going down by 24. And then down by 72. And then down 120. and then we're going down 168, and then we're going down, of course, 216. Okay, so I don't really see, this is going, it keeps going down. It's not linear, obviously. And I also want to make sure, remind you that our x's are consecutive. There's no gap, so we have consecutive integers. So we can just focus on the output. Okay, let's see if this thing has a constant second difference. So from 24 to 70, negative 24 to negative 72, that's going down 48. Down 48. Again, I can see that I have a pattern of going down 48. So this second difference is constant of negative 48. So this tells me that we have a quadratic function. And the negative 48 helps me find my A value. Okay, so we have an A, a B, and a C. Our A value was negative 48 divided by 2. So that gives me negative 24. So this is my A value. My C value is when x is 0. It's your y-intercept. So that is 600. So now we just need to find the B value. Now, I'm going to go through this, but remember this object was dropped. And I don't know if you recall from our quadratic unit, when objects are dropped, there is no velocity. Okay, so our A is going to be negative 24 x squared. We don't know the B term, even though I just kind of gave us a hint, plus 600. Now, we've already used the y-intercept, so we can't use that point. So I'm just going to pick this point to plug in for x and f of x. 1 is very easy to work with. And I have negative 24 plus 1 times b plus 600. I combine my like terms. And now when I subtract 576 from both sides, my b value is 0. So remember, when objects are dropped, you will not have a b value, which represents your velocity. So our equation is f of x equals negative 24x squared plus 600. And now we could plug in any value for x. Now realistically, the object is going to land in 5 seconds. So really, x values past 5 or before 0 are not going to be realistic. Okay, example number 2. Ben's swimming pool began leaking water. He called his pool guy Cash to fix the leak. Cash said he would charge an initial fee for taking the house call plus an additional charge for each hour he is there working on the pool. So what type of function would best describe the amount Cash charges Ben? And then we're going to write a model, which just means we're going to write an equation. So let's see if there is a first difference. Let's change colors. I don't think that is showing up that well. Okay, so our x values are consecutive integers. Now we can just focus on the pattern of our output. So here we are going from 200 to 275. So at 0 hours, he's charging 200. So I guess that's going to be our initial fee, 200. And then we're going up 75, and then from 275 to 350. So for an hour working on the pool, he charges Ben 275. And you can see that this is going up 75 each hour. So this does have a constant rate of change. Our first difference is constant. So this tells us that it is linear. And the 75 is our M value. Okay, let's write our equation, our model. So our M value is 75. So that's the hourly rate. And then our B value, the initial rate, at 0 hours, he charges $200. So I guess that's why they call him cash. He's fairly expensive. Okay, so we have a slope of 75, a constant rate of change. And then we could say, what if Ben needs cash to work on his pool for, let's say, 12 hours? Wowzer. So let's see how much the bill will be for Ben. Wowzer. So for half a day's work, it's going to cost Ben $1,100 cash. Thanks a lot, cash. Okay, Miss Thomas heated her passion tea at 300 degrees. Remember, guys, I have stopped drinking my coffee and now I'm drinking tea. Very tasty. After removing the cup from her microwave, it slowly cooled back to room temperature over a few hours. What type of function would best describe the temperature of the tea? And then let's write a model. Okay, so again, my x values, they are consecutive integers. So let's find the difference between our y values. So this looks like it's going down 60 degrees and then down 48 degrees. And then, wowzer, 192 minus 153.6 gives me 38. Negative 38.4. And then it's going down. So from here to here is 60, from here to here is 48, from here to here is negative 38.4. So let's erase this, make it put it in the correct place. So from here to here was negative 30.72. No. So from 192 to 153.6 was 38.4. And then we have negative 30.72. And then it's cooled down to 24.576. And then finally, room temperature, okay, it cooled between those 2 hours, 19.704. So obviously it's not linear. I don't think it's going to have a constant second difference with all these crazy decimals here. So let's try the new way and let's put a first difference compared to this difference. So a first difference compared to the previous first difference. So let's make some ratios, see if it's exponential. I'm just going to try a few. So when I have 48 compared to 60, that gives me 0.8. And then 38.4 compared to 48, again 0.8. So every time the temperature is going down at a rate of 20%, so our decay factor is 0.8. And because we're writing our equations, our exponential equations, in f of x equals a to the x, you can see our a value is going to be that y-intercept. So this is going to be the a value, and then this is decreasing each time by 0.8. So when we write that all together, we start at 300 degrees, and we're going down 20% each hour in temperature. So if I wanted to see what the temperature would be if it cooled down past room temperature, I could plug in 10 for X and calculate to see what the temperature would be. So let's just try that. And let's plug it into our calculator. And we get 32. So that would not be hot tea, of course. Okay, let's go. Now, the second part of these videos, we're not going to be given a function table. We're just going to be given the word problem.